Now we're going to talk about the metric system. So every value that we're going to measure is always going to have a unit associated with it. And that unit is just as important as the number. So if we look at some less scientific questions, how far away is Austin? If you say 3, that's not meaningful. 3 whats? 3 hours. You need to have that additional piece of information. How far away is Beaumont? 64. 64 whats? Miles. How far away is Huntsville? 152. Again, 152 kilometers. When you're looking at a value, if you're trying to convey a piece of measured information, you measured that distance or how long it took you to drive, you need to have that unit. And so it provides meaning. And one of the ways that happens, if you know what it is to be a mile away, so 64 miles away to Beaumont gives you some information as to what it would be like. You could certainly go to Beaumont for a day. You're probably not going to go to Beaumont if you need, dishwasher fluid, and you don't go to Beaumont to do that, right? You're going to stay local to do that, but you certainly would be more willing to do that. But Austin at 3 hours is going to be a bit more of an investment because you know what it means to drive an hour away. The kilometers may mean a little less to you because if you're not as familiar with those distance units, something being what's 1 kilometer, how far away exactly is Huntsville with those kilometers. So when you have a unit, it conveys information as to the relative size of a value. And so that's really, really important. If you don't include units, that is just as bad as having a wrong number, right? Without that unit, it's not important. There's no information. You need to include units on every single measured value. So when you're measuring things, there are different units that we can use. We saw on the last slide, we used time units and distance units to convey distance. Or time, how far away something is. You can also then convey different types of distance units, miles or kilometers. And so we have these different types of units for describing different sized things. So let's look at, if we look at length here, we can see that, something like an atom is extremely small. And so we'd want a really small distance unit. Something like a human or a blue whale is much larger. It makes sense to define differently sized units for those different things. If we think about driving, if I say it takes 3 hours to get to Austin, that means something. If I tell you it takes 10,800 seconds to drive to Austin, that's not as meaningful. That is the same thing as 3 hours, but because it's so big, right? You know how much a second is, but it's hard for you to imagine almost 11,000 seconds. If I just told you it's 11,000 seconds, it's not really clear how long that would be because the number is so big. So we use an appropriate unit to get a reasonably sized number. That's why we talk about driving to Austin in terms of hours instead of seconds. It also wouldn't be useful to talk about driving to Austin in terms of years, right? It's going to take you point something years because it would be so small, who knows how long that is. So hours is just right. It's not too small, it's not too big. It gives you a reasonable number. You can conceptualize what 1 hour is, and then you can conceptualize 3 of them. So standard system that we use in America is the customary unit, or there's slight variations in the imperial system or standard system. The thing about this unit system, for example, length, you can convert between different lengths for different distances, right? If you want to measure something far, we use miles. Something shorter, we use, say, inches. But the thing is, the relationships between all of these units are entirely inconsistent, right? It's 12 inches in a foot, 3 feet in a yard, 1,760 yards in a mile. Those are just numbers we can look them up and we can memorize them, but we'd have to do that. There's not really much rhyme or reason. And one of the real problems is you can't look at the word yard and the word mile and figure out the distance, the relationship between those distances. This isn't a system. This is just kind of a collection of units that have defined relationships. What we're going to use is instead the metric system. The idea of the metric system of units is that you have one base unit for a given type of measurement. So for example, in length, you have meters. So all distance units are going to be based off the meter. For reference, that's about just shy of 40 inches, about a yard. So, you may have in like grade school dealt with like a yardstick or meter stick. They're about roughly the same length, a little bit longer. Other distance units are then related by a power of 10. And we convey that using prefixes. So we can see you have your unit is always a prefix plus the base. The base in this case is meter. So we have, for example, kilometer or centimeter. Those prefixes, kilo and centi, correspond to powers of 10. So a kilo is 1,000. Okay, so a kilometer is 1,000 meters. Centi is smaller, so 1 meter is 100 centimeters. Okay, so a centi is a fraction of 1. So you need more than one of the centis to get back to the base. But all of the name is based on this, with the idea being you just need to know that meter is distance, and from that, you just need to know your prefixes. Centi is always 1/100th, so you can always use centi plus whatever the base is. So for our bases, we're primarily going to be concerned with meter, liter, gram, and second. So that's length, volume, mass, and time. And each of these units has not only its name, but a symbol. And so those symbols are abbreviations. It's just the first letter in all of these cases. And we always can use those. I do want to note liter, I'm going to use capital L for liter. That is more standard. There are a lot of people who use lowercase L's. So you will see lowercase L's. I try to always use capital L's to be consistent. That is the more correct, but sometimes you'll see people use lowercase L's, and that is, it's not really part of the rules, but so many people do it that it is accepted. Just want to give you a heads up, it is out there. So one of the things about these units is we kind of want to get an idea as to what is kind of a useful unit. So meter is a little awkward for measuring humans because it's about a yard. So a baseball bat is about a meter long, but humans are like 2 meters. So we generally tend to use centimeters, which are 1/100th, to measure human height. Mass is, a gram is really small. So mass is your measurement of gram. It's really, really small, almost 500th of a pound. So, 2 pennies are about 5 grams. So measuring human size masses usually are kilograms. It's much more common for us to use kilograms to measure people. And so in the lab, though, usually gram or milligram is more of a common measurement, because when you're doing chemistry, you don't necessarily want pounds of chemicals involved in your reaction. For volume, that's probably what most people are familiar with, which is liter. Liter is a reasonable volume to consume. So we sell a lot of beverages by the liter, which is very close, serendipitously, to a quart. So for our metric system, once we know our bases, it's just a matter of learning our prefixes. And when it comes to the prefixes, we can define them for very big. You can define out to trillion for tera. You can define pico is 1/1,000,000th. So these are all across. Generally, these are the 6 that we would use. And really the ones highlighted in blue are the most common. So kilo for 1,000, deci, centi, and milli for less than 1. Really, milli and kilo are the most common ones that we use. Centi really shows up in centimeters is the most common place. But so these prefixes, we can see there is a prefix. They similarly have a symbol that we want to know, and there is a mathematical interpretation, what they are, what size they are, right? Whether or not they correspond to 1,000 or 1,000th. And we want to be on top of that and know those things. And yeah, the ones that are higher, we will come back, nano will show up again, but there's other ones we don't really use. Some of them do have commonplace use. Tera, giga, and mega correspond to the size of files. Byte is the unit for the size of computer data. So megabytes, gigabytes, terabytes, those are metric prefixes that you're using. And tera is 1,000,000,000,000 bytes. So what we want to get comfortable doing is relating different types of metric measurements, where we have different types of sizes, and we want to be able to complete these equivalences. So 1 millimeter is how many millimeters kind of stuff. And so when we're faced with something like this, Our first idea is always going to be, well, what's the prefix and what's the base unit? Because that's the whole idea behind metric, is that we have this prefix and we have our base. We can interpret that prefix. We can interpret that using this table, right? You do want to, you're going to just passively learn those middle six. I would encourage you to learn those middle six, but you can also always look it up. We can look these things up. The problem with if we start to look up everything, we just are really slow. But for now, we can look these things up. Then we want to balance that out. Once we know what the prefix is, we can relate it to the rest of, we can turn it into a number functionally, and this becomes like an algebra problem. So got a couple of 5 little examples here. Let's see what that looks like when we actually work them out.
So we've got these metric conversion factors that we want to complete here. And so when I have this, if I see that this is 1 is equal to something m. So the first thing I can parse out is all of my metric units are made up of 2 parts. I have the base and the prefix. And so if I have 1 letter, that's always going to be my base. So this means that these are meter. So I know that that little m always means meter. Then the little m in front of it is then going to be my prefix. And so if I want to interpret my prefixes, I can always just look them up and I can see that little m is milli. And so this is 1 millimeter. And I can literally just look up what milli means numerically. It's 0.001 or 1,000. Okay, so milli always just means 0.001. So I just take that number and it goes into that slot. You can see that basically the prefix is the same as 0.001 of your meters. So milli leads to a 1 millimeter is smaller than 1 meter. Similarly, mg and g. That g is my base. So this is now gram that I'm dealing with. And I would interpret the prefix in the same way. I look at m. We can see that the prefix is still the same m, so it means the same milli. Okay, and so that means the same number, 0.001. So 1 milli of anything is 1/1000th of the base. I can change my base to L, which is liters. But that's still the base. And you can see when we're looking at these metric relationships, we can see that my base never changes. The base doesn't change. M, G, and L stay consistent whenever you're doing that. The only thing that does change is the prefix, whether or not you have one or not. K is a new prefix here. K is kilo, which means 1,000. Kilo is 1,000. All around the world today. So kilo, 1,000. And so whenever we see that 1 KL would be this. So we can see that these are just generically true. In much the same way that milli, didn't matter if it was millimeter or milligram, it was 1,000th. A kilo, it doesn't matter what you're measuring, will always be 1,000 of that thing. All right. So that's just interpreting prefixes. Here we've got a slightly different thing. I've got 1 gram equals 1,000 watts. Sorry for the typo there, but so we want to fill in what that unit is. Okay? So we know a couple things about the unit. We know it's gonna have a prefix and we know it's gonna have a base. So we're looking for 2 parts. And we know the base is not going to change, right? We've got grams. Our unit needs to end with grams. So this is gonna be, what we're looking for is something grams because we started with grams. And so what we can do is we can kind of set this up as a algebra expression where I have 1 gram is equal to 1,000 times some sort of prefix grams. And we know those prefixes have a numerical meaning, right? They have a numerical meaning. So what it would be is it's 1,000 times what equals 1, because the grams don't change. So 1 is equal to 1,000 times whatever x is. We can say that x is equal to then 1 divided by 1,000, which is 0.001. Okay. And so that number, if we look it up, that number, that mathematical meaning is milli. So what we can do is we can say, well, this means that our prefix is milli. So this would be a milligram or milligram right there. Your gut instinct when we said 1,000, I bet you many of you said kilograms, because that's kind of a standard kind of when we see that number 1,000, we think of kilo, which is good that we're learning our prefixes. But one of the things we can see is that 1 kilo is 1,000 of the thing. 1 gram has to be 1,000 of a smaller unit. So we can see if you have more of something, that has to be a smaller unit. So the milligram is smaller than the gram. The other thing we can start to see is that for a given pair of units, there are two equivalent or two equal expressions here. That we can either have 1 gram is 1,000 milligrams, or 1 milligram is 1,000th of a gram. You will note that the numbers are always different by an order of 1,000. The smaller number is always next to gram, and the bigger number is always next to milligram. Both of these will work, and you can use either. These are sometimes easier to represent or come up with using the prefixes. These are more commonly applied by people just because people don't like decimals. So you oftentimes see that 1 gram is 1,000 milligrams. But you could also say 1 milligram is 1,000th of 1 gram. Last example, 1,000 L is equal to 1,000 watts. If we look, this is the exact same setup we had right here. So it's going to have the exact, if we work through this problem, we did this kind of analysis, the only thing that changes is all these G's become L's. The base unit changes, but the relationship of the math and the prefix has to be exactly the same. So our answer has to be milliliters. 1 of your base unit is always 1,000 of the milli of that base unit.